This is all without us seeing anything, right? All hidden. But lots of bad things are happening here. I'll show you even more consequences in a second. Finally, we see it, and we'll see it as flooding at creeks. We'll see it as flooding over storm drains on streets and storm drains in parking lots, and we're already seeing that. I can go down at high tide to parking lots along the bay edge and see that the drains we put in to take rainwater away are causing spot flooding. I can see it on streets in the city of Alameda. I'm a little bit ghoulish. At high tide, I'm like, oh, this is happening. Because people need evidence to understand.
So the drainage system is now doing the opposite.
Because it's a void, it's so much easier for water to move through the void of the pipes than it is to move through all the friction in the soil. It comes right up through all the drains. It's happening here, New Zealand, Hawaii, New York. Just the places that I, have been to and seen it happen. So the saltwater wedge and all this change is happening in spite of the levee. This is my point. All this whole idea of using levees and seawalls to keep out the effects of sea level rise, it's only going to help with the waves and the lateral movement of high tide water. It's not going to help with this whole other dynamic of rising groundwater.
When did you say 3+ feet was going to happen?
By 2070, I think, 2075. Yeah. And we know that now that's the minimum by 2100. 3 feet by 2100 is the minimum. So that would be the maximum amount of time, 75 years to get to 3 feet. And geologically speaking, this is what I love. These are the visualizations that my people use to try to understand what's happening. So I'm going to show you this shoreline of contaminated sites in the city of Richmond, because I know a lot about it. Right now, there are rivers that come out from Wildcat Creek that go out to the bay right here. But this is like the Louisiana Delta. There used to be a river that came down here. And then there was a time when it came down here. And there was a time when it came down here. And it left these gravels and sands in place. That's what rivers do. They sort material, and they leave you with sediment that's like an old riverbed. We call it a paleochannel. And Richmond is covered by these fingers of paleochannels. And the sites that are contaminated are down here, right at the tips of the fingers, where the artificial fill is, which is shown in pink. There's even a potential geologic fault. But this pink artificial fill is everything, Volkswagen-sized chunks of concrete plus brick rubble plus clay plus sand plus wood plus sometimes metals. It's everything they had as waste that they dumped into the bay to try to extend the land for industrial use. There's a little freshwater marsh or a saltwater marsh here and some freshwater marshes up here, but mostly it's this artificial fill. And water is being conveyed, groundwater is being conveyed down these, they're like a pipe. They're carrying water from the hills out to the bay underground, like a pipe. They're a preferential pathway. And they bring that groundwater right to the contaminated sites that I want to talk about.
That's currently happening.
Just finally getting a model of this specific area by a student at the University of Arkansas, so it's taken us a while. And these are the contaminated sites along there. In the red, those sites are still considered administratively open because they have a lot of waste material still present. And they're all over rising groundwater. That light blue zone with the contour lines on it is rising groundwater. That's within, I believe it's, 10 feet of the surface. And that is a really important distance. Most people are talking about groundwater as a danger when it emerges. No, it's a danger way before it emerges because this site here, let's see this one, has had material piled up on it to become a new building site. So it's had maybe 8 feet of material piled up on it. That's fake elevation. The waste is still 10 feet to 20 feet down. So what matters is the depth of the waste, not the surface of the land. And yet people are doing these maps and saying, oh, look, we're 10 feet above sea level rise. We're not going to, be affected by sea level rise. Well, yes, they are going to be affected. And this is where those fingers are that bring groundwater down to that contaminated shoreline. So it's intense. What I think is happening is that all this water is coming down, and when it meets the artificial fill at the end of the fingertips, the water backs up because it's moving through a pipe and it's hitting material that's not very conductive. It's all different sizes, doesn't allow a lot of permeability. So I think it's actually higher at the edge of the artificial fill, and we're just starting to get data to be able to look at that. This is what that landscape looks like from a drone. And at a king tide, at a high tide, you can see that it's the water is very high. These are old waste lagoons. They're now called habitat areas in a kind of Orwellian speak. And this is the old chemical factory now owned by the AstraZeneca company, not a poor company, a very wealthy company since the vaccination era. And these ponds actually spill over into the cities here. I'll show you what I have up. This, when it fills up with rainwater at high tide, it backs up into the sewer right here. So this contaminated water is going into the city's pipes. And these lines, the little hair-like lines, is another visualization we help with. They start at watering wells. So each of these little clear open circles is a spot where we know that there are dangerous chemicals. And this is the sewer system, the sanitary sewer system, that's connected to buildings. That's a very, very important difference from the storm sewers. They are not connected to buildings. They're just connected to the street. The sanitary system comes into your house. Anything that's in that pipe could potentially enter your house if it's a gas, because gases go uphill. So all these little hair-like lines are the flow lines on the groundwater surface. The groundwater surface is like topography. You can predict where things are going to flow using the contour lines, just like you would predict where water is going to flow on the surface of the land. So we predict where these things are going to go, and every time you see them crossing the sewer pipe, these little skinny black lines cross a sewer pipe, that's a point where these toxic gases and the liquid can enter the sewer pipe and then enter buildings.
Are there examples of that?
Yes. And we measured, maybe I should just talk about it now. So here's a sewer pipe, and it's connected to a city pipe. There are other points where we think they're going in this direction, but they may actually go here. We sampled on this sewer pipe, a building owned by the University of California, Berkeley, right out there. And we found extremely high levels of two toxic chemicals that cause cancer in the sewer cleanout, which is where the plumber goes into outside the building to check if the pipe is
Which chemical?
TCE and PCE. TCE has just been reclassified as very, very hazardous, even in small amounts. And for people who are in developmental stages, a person who's pregnant, or a child going into adolescence, or just growing, that's really critical not to be exposed to VOCs at that time, because it has lifelong implications if it affects reproductive organs. So, super important, and we found it. And we went to the state water board, they told us, well, it's not the smoking gun. We're like, well, why is it not the smoking gun? Because the only thing keeping it out of the building is a seal under the toilet. And those crack over time, they break down. So they said, well, if you had it in indoor air, it would be a smoking gun, but you have it in the clean out, outside the building. That's where it's gonna go, it's gonna go to indoor air.
So all those chemicals are from previous industries, or?
They are,
Those
this is
lines?
just showing the water from that lagoon going into the sewer. I feel like I need to have evidence for everything they say. Could you say
That's
that?
good.
The hairlines of the chemicals, those are from previous, like,
That's
building
from previous
industry?
manufacturing of chemicals
Hmm.
on that site. They
I see.
made sulfuric acid, They made agricultural pesticides and herbicides using persistent organic pollutants that never break down. They played around with uranium. They had a uranium furnace there in the 50s when everybody was trying to find something fun to do with uranium. And they used all kinds of solvents, and those are the TCE, PCE chemicals.
TCE and PCE.
And what companies would this have been, and is there any chance of getting money from
Yes.
the company?
Stauffer Chemical was the original company. They were there from the 1910s, I think. They sold the site to AstraZeneca, and now AstraZeneca is on the hook. And AstraZeneca has a lot of money. So it's not some mom and pop dry cleaner that nobody wants to sue.
And you say they're on the hook because they're responsible for
They are called the PERP, potentially responsible party. They are legally responsible for what happens to this site, and if it causes contamination off-site or on-site. So they are a huge target.
And they must have known that when they bought.
They knew that when they bought it.
So, I don't know, even though they have a lot of money, if I was that company, I would have said, do we really want to take this on? Or were they just like, oh, no one's going to ever take us to court?
When they're under pressure to clean it up, they can. The University of California at Berkeley was going to go into a development agreement for this site. It was called Campus Bay. They were going to do a new international campus. This is not hundreds of years ago. This is 5-10 years ago. And at that time, they had a price estimate for cleaning up both sites completely, taking out all the contamination, physically removing it, $127 million. Drop in the bucket for AstraZeneca. Yeah. Even in the price of doing it, that was not considered prohibitive. They were just going to do the project, and they would take out the contamination. And they used to say, well, you can't take out contamination because then trucks have to drive through the neighborhood. And that's really hard on people, all that truck traffic. But they can do this by barge. They can take out these contaminants at the water's edge by barge.
And where do the contaminants go after that?
We need a regional treatment facility. That's what everyone says. Well, you can't send it to Cattleman City into some other poor neighborhood. Well, you shouldn't. But you can sequester it. You can put it in big concrete or plastic boxes. You can treat it, just not on site. They can run electricity through it. They can run water through it and do a pump and treat. And you can separate it. You can have a facility that does separation, so you take the dirtiest stuff and you treat that or sequester it. The middle stuff you make into building blocks. You really pour it into concrete. Or if it's radioactive, you pour it into glass. Pour glass around it. That's vitrification. And then if it's not that dirty, you just start using it as a coastal habitat material. So it needs to be sorted. And we need to deal with it. And we have lots of facilities around the Bay Edge where we could deal with it.
So what happened with, if we have the number of how much it would have cost, 5 years ago, why didn't that?
Because the university decided not to go ahead with the campus development. The chancellor was voted no confidence, he's out of there, budget crisis, and now it sits there, and oh yeah, this is the kicker. Now Zeneca is going ahead with their own redevelopment of their own portion, not the part that UC Berkeley owns, although the two have become a legal entity called Campus Bay, and the lawyers for Zeneca will prevent anything from happening that would affect them on the UC Berkeley site. Now they're all sharing liability for the contamination together, the university and Zeneca. I know this because I've gotten threatening phone calls from the university about things I say about the Zeneca site. So the Zeneca site has gone ahead and gotten 4,000 units of housing permitted for that site. This site, the flat gray area.
Sorry, Zeneca has.
Huh?
Zeneca has got.
Zeneca
Approval for
created
housing.
a shell company, child
Okay.
company, and that company took a proposal for housing to the Richmond City Council at a time when there are a bunch of relatively conservative activist or housing people on the developers really on the city council, and the mayor, and they gave it a permit, and it's very hard to take that permit away. So now the city council has gone back to a progressive group, Richmond Progressive Alliance, and they are trying to undo the permit by showing evidence like what we're finding about how this site is leaking contaminants to other sites adjacent.
Like a soccer
Yeah, we have a soccer field in Berkeley that's on
field. I know.
a landfill site. So that's what's coming. And they're doing kind of an acupuncture version of cleanup, which is not working yet. They put pipes in, they're trying to suck vapor out of the soil vapor extraction system. But it's getting too wet because the groundwater is too high. So if it's wet, it can't pull gas out because it's just pumping water. I'll speed up a little bit. So I look at places around the bay, Richmond, South Bay, Oakland, San Francisco, all these little ant-looking black dots are open, contaminated site. There are more than 1,400 around the whole Bay Area, and they're in the most urbanized places.
Is that common for countries to do this, or is that quite unique to the
To have
Bay
a
Area to have all this kind of toxic waste kind of just?
Everyone has the toxic waste. Very few countries have the map.
Okay, so London, as an example, would probably be doing this as well.
They have contaminated wastes in the soil all over.
Yeah.
Everything humans use, we spill.
Your shirt.
Yeah, everything we use, we spill. So if they're using solvents in London, they've spilled them somewhere.
Yeah.
If there's ever been a military base, it left fuel behind
Mhm.
and other solvents. So it's everywhere. It's everywhere around the world. Every industrialized place, and even less industrialized places where there's, for example, oil and gas extraction happening, someplace like the coast of Nigeria, is going to have this problem, but it'll be petroleum products.
What does the policy look like for manufacturing companies right now in terms of?
Now it's much stricter. They used to stockpile wastes in big 55-gallon metal drums, and those would corrode. Surprise, surprise. And then it would all go into the ground. Because there was no money behind it. Once it's a waste, nobody wants it. So they ignore it, and then next thing you know, it's in the soil.
But one of your solutions was, you were saying, to put it into concrete.
That's one of the things the Germans have done.
But isn't that going to corrode?
It won't if it's dry. So you'd want to put that kind of concrete high and dry. And usually they're using metals, or they've broken the chemical down in some way before they do it, before they put it in the concrete. It's a great way to get rid of something like chromium, but not a great way to get rid of volatile organic chemicals, gases. So here's a diagram that I use. I really wish I had something to explain better. Where
We'll help you make one.
Nudge.
the VOC plume is floating, it's typically lighter than water, and it floats on that dashed line, which is the water table, towards the sewer pipe. It gets in the sewer pipe, and then it off gases. And now this red thing is gas, and it comes up through your plumbing and enters typically through the seal cracks at the base of the toilet. I had to fight it with the mayor of Richmond at a city council meeting, who said he's an architect. And he said, he thinks he knows, about toilets. He says toilets have a P-trap, so they can't allow sewer gases into the house. Yeah, but the toilet has a P-trap that's in the interior. It's incorporated in the toilet. It's not in the floor. The sink has a P-trap that's usually in the floor. Sinks and bathtubs, but the toilet has an interior P-trap, so that's usually where gases enter the building. And through cracks and slab foundations, and through plumbing pipes that weren't stubbed properly that are still open. A lot of people have those, old houses. So older, less well-maintained buildings, schools, workplaces, houses are going to have this. Multifamily where people are renting. And they don't change their own toilet seal. So it's about maintenance. whether this is happening or not. That little stub thing there is the cleanup. This is what we've been measuring in. You pull cap off, you put a little metal tube in, and you leave it there for 2 weeks, and you can see how much gas there is. Different kinds of gases. And the VOCs can travel as far as 750 feet uphill and 2,250 feet downhill. So we're trying to model how far they can travel based on those two rules. If it's uphill, it's max 750. If it's downhill, it's max 2,200. And they found that out using tracers, so that's experimental evidence. It's not theoretical. And we sampled, there's a map that shows big TCE and PCE plumes here. This is the Zeneca site. This is the UC Berkeley Richmond Field Station, where people are working in these buildings, many of them. There's a plume here, which means a big puddle of these chemicals in the soil. And there's a sewer pipe right here. And this is the building we sampled the cleanout for that has very high levels of TCE and PCE. So it's attached to the sewer line, which comes past the plume. Even though we think most of the contaminants are moving towards the bay, something has moved into that sewer pipe. There's no other source of TCE and PCE in that area.
The art studios are right there.
I know, our practice is in there, down here at the lower part, right? And we didn't find anything. We looked in that building. We wanted to make sure we were protecting people, so we did sampling in the buildings we could get access to. We didn't find anything in the buildings except cleaning product stuff on the Richmond Field Station site, but in the cleanouts. I don't want to start a rumor because I know there are a lot of people who are using those buildings. So now let me share more bad news. Here's our salty groundwater, right? And here's our fresh groundwater. I mean, this is the mixing zone. It doesn't mix much because they're different densities. And here's the fresh groundwater. And here's the foundations of a building with pile foundations. Here's some contaminated soil on a dry creek bed. And here's your storm sewers and your sanitary sewer pipe connected to the building. And there's a levee. I always include a levee just to make the point that it doesn't matter. As sea level rises and that groundwater rises, the thing everyone starts doing is pumping. And it's currently unregulated. No one knows whether you have a pump in your building. People are doing it. My neighbor just put in a sump pump. Everybody's doing it in these flat places where groundwater is shallow in the winter. So when you put in a pump, this is something we learned from the Dutch. So let me say first, this is all we've talked about so far. The sea level rises, and then the water rises up the soil. It mobilizes contaminants, and then those two black vertical things, those are meant to represent pumps. So we get the inundation and the legacy pollution. We get the change in flow direction because of the pumps. So the pumps are now pulling groundwater towards the building and the sewer pipes. As soon as you put in a pump, you're changing flow directions on what's otherwise a flat surface. You're pulling it real hard into the building. And you start getting this phenomenon shown here where the dark blue is inundating the foundations. It's called upconing. The Dutch have known about it for 100 years. They call it the Geiger-Hertzberg principle. It's in all the textbooks that people read in groundwater hydrology. When you pump the groundwater down a foot, you pull the saltwater boundary up by as much as 40 feet. 1 to 40 is the ratio. Because you change the density relationship, you release a lot of pressure on that salty groundwater that's more dense, and it rises real fast. And once it rises, it does not go back down. So that changes the conditions that the building's foundations are in that probably were designed for fresh water, not designed for salt water. You have to do thicker concrete on the rebar of a foundation pier that's in salt water. Because the salt ions penetrate the concrete, the rebar starts to expand as it rusts, and then you get more cracks and faster corrosion. And if you remember that Florida condominium collapse near Miami that killed 90-something people a few years ago, they think that this is what happened in addition to some design errors. That the foundations were exposed to salt water and corroded much faster, and you can hardly inspect them. How do you know? Now Miami-Dade County has the only required foundation inspection program in the country, but this is happening in every coastal city.
So when they build big skyscrapers like in San Francisco, they cut out the foundation and for months they're just pumping water. Is that just like deregulated? I mean, that's just legal.
You're dewatering your site for your construction process. But in the process, you're pulling up the saltwater boundary. So the downtown core of San Francisco must have salty groundwater under the buildings, mixed in with all of the foundations and pipes. And other cities, small cities like San Rafael, the Canal District, they have salt water. I've seen it. So they are pumping stormwater. They think they're only pumping in the wet season, but their pumps are on automatic. And so they go, every time the water rises, they're pumping all year long throughout the summer. So they're bringing up salt water. Anywhere we're pumping, we're bringing up the saltwater boundary. And so we're exposing our pipes, electrical conduits, building foundations, bridge foundations, everything is in salt water.
Good news is the next slide.
So I have been thinking, what do we do with this? And in fact, I had the idea for what to do about this before I knew everything that I know now, but no one would listen to me. So I put my Dr. Doom hat on and went out with the science thing to try to show everybody what's happening and have data and evidence. But this is what I was originally talking to people about. So if we use landforms, if we manipulate landform as a way to adapt, and this is what the Dutch have begun to do, they've been working on for a while. As the sea level rises, so let's start with today's situation. You've got terrible foundations now corroded in groundwater. When the earthquake happens, let's hope it's not during this meeting because we're so close to the fall line. When the earthquake happens, these conventional buildings are going to fail. More of them than we expect because of this standing in saltwater problem. And we can take those areas where there are conventional buildings, dig out the material, some of which is contaminated, and use that clean part that you can cut to add to the marsh on the shore zone. Build your levees around your pond, small levees, modest levees, because they don't have to do much. They just have to keep the waves out. And then let the pond fill up, let the cut area, the excavated artificial cut.
Earthquake?
Civil defense.
That's our Wednesday drill.
Watch out! Eddie! Yeah, we're in the wrong place. So, the idea is you cut and you fill, you balance your cut and fill, and you put a filter park on the uphill side of your pond. So that the rain coming off of roads and off of conventional development gets filtered before it goes into the pond and before it goes into the bay. So you have to pay attention to your water quality, otherwise your pond is a toxic soup. So you have to cut away the polluted soil, keep the pollution from going into the pond, and then you can develop. And then as the sea level continues to rise, you can move this band of ponds inland as these conventional buildings start to fail that are farther inland. So it's phases of managed investment. I don't call it retreat because everyone hates that. No one in the United States will listen to a talk if you say managed retreat. Don't even bother. So managed phases of investment, because this can bring private dollars into the adaptation process. And we used this illustration at a competition in 2018 where we won the prize of being most Dutch. That's a good prize. We want that prize. But we were saying that we can take areas where there's a tributary coming into the bay, a creek, and these are the most difficult for conventional adaptation methods. You can't build a levee across the front of that creek because it will just fill up behind the levee and spill over and cause flooding everywhere. So it's difficult for conventional methods, and yet it's perfect for this pond idea take your cut material, you place the clean stuff to make a bigger wetland. And if this river, when this river has a high tide and a heavy rain at the same time, it just floods into your ponds, and everything in the ponds is on shared decking and floating. And this is what the Dutch are already doing. So I could take you on a tour to Amsterdam right now and show you how they're building a floating district. And there are affordable as well as expensive versions, subsidized in different materials and stuff. But that would be what I call a band of ponds, and that band can move up. And students have done studies in my studios over the last few years, and we keep talking about how really it's a combination of pond plus canal, because the canals do a lot of work in the Netherlands, and we need more canals to manage our groundwater and provide us with access, potentially either habitat or actual transportation, depending on the size. Let me show you how a canal works. Here's a visualization. My students make these plexi models, and then we put water in them to show how they work. This was a good one because they edited it well afterwards. And see that white line rising? It's going to rise the same way on both sides as water is added. And on the canal side, on the right, there's a little hole in the plexi wall. You're going to see that groundwater come out the hole and down the front of the plexi, starting now, I think. So now that water is running out of the plexi model onto the deck there, and not on the other side. So the other side, the groundwater continues to rise. There's no canal. On the canal side, the groundwater stops rising.
So this is like what they have in Amsterdam.
And they actually pump their canals, because if you don't pump the canal, it doesn't pull the groundwater out of the adjacent soil. You have to wick it. You have to create a positive pressure to pull water out of the soil. But we could be doing this in neighborhoods like East Oakland or San Rafael Canal District to let buildings stay in place for longer. Let's say it's an African-American neighborhood where grandmothers own the houses that their parents own, and the kids want to receive them. It's the only property the family has. You're not going to say move to an apartment. You're going to want to help them stay in place for another generation. So canals could help people stay in place and can protect soil for agriculture.
But it will stay in place for longer,
Not forever.
Yeah.
Because eventually you'd have to pump so much that the power and the fragility of the system can't be justified.
Has this work happened at all in like New Orleans?
They have pump stations that pump over the levee, and they pump stations that are the size of a university campus. And they have huge tubes that are the width of this room. The length of this room is the width of the tube that goes into a big pump station with huge turbines. It's a big deal. It's industrial scale pumping. Otherwise, New Orleans would be a lake.
The initial drawing you showed of the bed of ponds, and you're building these, so that's human-made marshland that's create wetlands coming out from the coast?
Yeah, that's what we're doing now. We're already building those marshes. So I'm saying add the ponds and the canals. We're already building the marshes.
So eventually, say like the whole world took this initiative and we start building more land mass, encroaching into...
Well, as the ocean is rising, we're not really going to be building a delta out. We're going to be building the shelf of the shore zone a little higher as it moves inland.
I see.
So we'd be doing a little bit of what we call shallowing now to make those marshes, just for habitat. And we're cutting artificial ponds. Here, let me show you.
Okay.
So this is the proposed that the students did. So that's floating decking. That's not ground, and it's not on piles. Some of the pieces would be attached to piles, but it would rise and fall with collars on the piles. You know how ferry docks do? There's a collar around a fixed pile, and it goes up and down with the tides. That's the idea here, is that these would be tidal. And as the tide rises, it doesn't affect the buildings because their portion of the decking is rising. Portions that need to rise, and we can get to 3 feet of sea level rise, and our landform is intact, the decking is intact. if there was an earthquake to happen, maybe the landform would break a little bit, but all it would do is let more water in and everything would still float.
Are they harvesting energy from that tidal movement?
They could, but you need a lot of tidal movement to get energy.
Radios.
But this is still only to 3 foot, and
Yeah,
then
so this is 6 feet. Now you see the berms around, or levees around these ponds starting to look kind of tenuous. So they need to be built more robustly or added to as we get to 3 feet and 6 feet of sea level rise. But if I had already invested in that prefab housing stacked on decking, I probably would go ahead and raise that landform because it's worth it. You've got it all there already.
so
But after 6 feet, I think we wouldn't be able to keep the pond. So that's where we hit the point where we need a new band of ponds. And we're trying to illustrate that here, that the marsh itself it's been added to, the elevation of the surface has been raised, but the sea starts to come up into it. And the ponds are here, and the canals, and we start adding the next group of ponds and eventually fill. So from this cut, ideally, we would fill these ponds so that they become the new marsh.
and because those houses are floating, you can transport them to the next
You
pond.
could, if they're worth it. I mean, if they're wood prefab, wood frame prefab, they may not be worth it. 50 years in the future, it might be better to do new
Yeah.
ones. But the
Japanese style.
decking material might be some wood, metal, composite, foams. I don't know what the materials would be. So you could probably take a modular decking and bring that to the new pond. And it would all be, I mean, we've been talking about sizing things to be movable by flatbed trucks and cranes. So I think it's doable. And then the architects made, on our team, as David Baker Architects, made this illustration to show what the pond would look like with buildings on it. They're not showing all the pontoons that would have to be under the decking. Pontoons would be probably 6-10 feet thick, depending on, because you have to displace the amount of water that represents the weight of the decking and buildings.
Is there a pilot neighborhood that is going to do this?
We got permission, well, I didn't. A guy who had patents for this kind of development using shared decking, graduate of our college, he got permits in San Jose, in the El Viso area. And then COVID hit and the development money went away. And the developers are reasonably worried that they're not going to get permission from the state or the federal government to do it. They won't get insurance for a new kind of unconventional development, and they're worried that their money they'll just burn money waiting to get all this to happen. So we need to open a pathway for this, and I think we need to start with something small, like a floating hot dog stand, and just show people how fun and great this is. I mean, that's what the Dutch do. They do a bunch of stuff to the landform, put sand in or take sand out, and then they bring some shipping containers over, hang strings of lights on them, have a band come and play, turn one of the shipping containers into a bar, and next thing you know, people are excited about the adaptation project. So I've learned that from them. You have to make it into a bar.
Yeah.
Bring people down, get everyone excited about it, give it a name, and then it gets momentum, and it might actually happen. So we have been doing these plexi models and trying to show people how floating works. Americans aren't sure that heavy things will float, just like they're not sure about the metric system. The Netherlands, but well, we don't have the metric system, so we can't float things. It's strange logic. So we need to show people stuff. I mean, this is the region where we build concrete ships. We know concrete floats. And I feel like demonstrations and visualizations could really help us get there, along with maybe taking people on tours of, in London at the Victoria Docks, the Dutch have tugboated a 3-story hotel into place.
Okay.
It's floating at the Victoria Docks, 300 rooms.
I love that. Is that like a little arm that pivots?
Yeah,
The whole
because you
building?
have to have a ramp. And you'll see these at ferry docks. There's a ramp with a hinge on one end and wheels on the other. So that you can go up and down with the tide. and the ramp adjusts. It's so cool. So we're trying to explain mechanics, because people said things to us like, well, how will you get to it at low tide? How will you get to it at high tide? The same way you get on a ferry at low tide. We don't live at the ocean anymore in that way. Like, we're not used to the mechanics of tides and keys and access. Floating. So I've seen the Dutch came to this competition that was run in 2018, and they proposed housing on the bay. This is a non-starter. You will be dead in the water if you propose housing. They're trying to get rid of all of the houseboats that are on the near-shore, shallow water environment because they're blocking sunlight from reaching plants and allowing habitat to exist that's really critical. So I'm talking about the other thing the Dutch do, which is excavating artificial ponds. And that's how we can work our contaminated soils, coming full circle. When you pull the contaminated soils out, you leave a hole. You need to fill a hole, and then it'll fill with water. And if it fills with water, we can put floating districts into it. Or managed habitat, or recreation, some mix. So that's what I'm hoping will come out of all this. But I started with this, and everyone said, oh my God, that is science fiction. They're very polite to me down in Pebble Beach when I presented to the developers, but they thought it was science fiction. So now I am working the science side to bring everybody around to why we have to deal with this groundwater and contamination problem. But I think this would be the way to deal with it.
No vision. It's so hard for them to envision things. And do we have any historical precedent in the United States of floating housing?
We have a lot of houseboats. And there are, as I said, patents for buildings that would rise and fall in, you don't even see the water. They're in a cut area with a pontoon. And it's even a proposal for historic buildings. In fact, there's a Canadian architect named Elizabeth English, and she has done floating wooden buildings in the Louisiana area for African American communities where their church is at risk of flooding. So the big communal building gets a pontoon under it, and they allow it to rise and fall in basically a foundation hole.
Would it be cool to make Market Street a
I think it would be cool.
canal?
Ferry building, they're gonna raise that, 8 feet? They should float that sucker. We have a floating fire station in San Francisco. At the Bay Bridge, there's a new fire
Wow.
station.
Yes.
that's floating.
True, on that barge.
And you can take people onto that.
Amazing.
The Dutch don't use a barge. They use a pontoon that you can live in when they do individual structures. You can't have a bedroom in the pontoon level of the 3-story building. You can have living space. And now with the new floating decking, it's the decking and the pontoons below, and then you just play a stacking game with prefab on top. You can stack as much or as little as you can support. And you get public space because you've got prefab units and stacks with space in between.
What's the difference between the barge and the pontoon?
The barge is a solid, and the pontoon is usually a void. Might be filled with foam, something low density. But the barge is a solid.
And if you did things like iteratively, like all these buildings on Market right now are boarded up and maybe they need to be taken down. If you took one down and dug down and created a pond and just kind of did that every time you needed to demolish a building, is that a approach?
You know, there's a spot in San Francisco, it's at 5th and something. I can show you where. There was an article that showed up in the paper about a pond spontaneously formed at this vacant site that has leftovers of a foundation of a building. Remember reading about that? That's groundwater coming up at that site. It's very shallow there. And it was in the winter when it rained a lot. the water table came up and flooded that site from below. So that's where I would start, someplace where it's already happening.
Yeah. Because in Brussels, where I'm a lot, and in Rome, that was happening naturally, and because maybe it's different policies, groundwater is so precious that it took precedent. They couldn't build anymore, so they had to create these kind of preserved areas where they were going to build.
And they couldn't do what to the groundwater? They couldn't pump it? They couldn't
They
build
just-
stuff in it?
Like in Rome, groundwater is like super
Because they're
precious.
drinking it.
Yeah. And this area they were going to build a super mall. They started construction and they hit the groundwater and it just filled this whole area. And
Yeah.
so it's now a nature preserve.
We can do it because we don't drink that shallow stuff. That shallow stuff is dirty.
Okay.
Good luck to them. It's got everything in it off the streets already, right? It's connected to the surface. But we drink water that's below a clay layer or a rock layer and brought up by pumps. We don't, nowhere in the US, except maybe Florida, is anybody drinking water that's connected to surface water directly. You have to treat it a lot. Well, no, we drink it. That's not true. The Mississippi River is a lot of millions of people's drinking water source, but they treat the crap out of it. Excuse me. It's literally true. So they say that the Mississippi River, by the time you drink water in New Orleans, it's been through 10 people's bodies. By the time it gets to you. And we should be embracing that, right? Singapore is treating wastewater and calling it new water. So that is the future.
So you made this map of all these contaminants, and I've looked at it a bit, and but not for a few months. On the map, does it associate the contamination with the companies that?
No. We have a new study that we're finishing that's 21 sites, all of which have volatile organic chemicals. And I really want to emphasize it's the VOCs that are the pressing, immediate danger of coming into houses. A lot of other sites have metals, chromium, other kinds of things. And that will mostly travel downhill to the bay, to habitat areas. And people could get it by eating fish or shellfish, playing in the soil, doing construction work or maintenance work, but they won't get it in their house. It's really this gas, liquid and gas together, the volatile organics. That's the super pressing thing. So these 21 sites all have VOCs. And we're studying the whiskers of sewer pipes that come away from those sites and identifying all of the buildings. So we can show how many schools. It's about 22 schools that are attached to sewer lines for these 21 sites. And it's places like everything from San Quentin prison to places in the make-believe wonderful city of Alameda, where everything is good. Here in Berkeley, East Oakland, and West, it's all over the Bay Area.
Can you talk about the difference between a closed and an open site and what that
Yeah,
means?
it's just administrative.
Okay.
They've decided that there's no reason to monitor anymore, and so they close it. And they even sometimes take out the monitoring wells. Because they say petroleum products, it's true that over 10 to 15 years, soil microbes will break down the leftover product, petroleum chemicals. So over a period of time, they do break down naturally in the soil. They're not the big worry. It's the TCE and the PCE. It's the chlorinated VOCs, sometimes called CVOCs. That's the stuff that persists and travels uphill.
And silicon wafer making, was that VOCs? Silicon wafer?
That was VOCs, yep. I think it was TCE. In fact, a big plume down by the Google headquarters. And they had to close one of the Google headquarters buildings for a few days to test indoor air, and they said it was fine, but it's probably in the toilet, the sewer cleanouts.
What was that? Silicon wafer, there's like 29 sites in
Some
South
of the
Bay
original Superfund sites.
that made the silicon wafers,
Chips.
computers, and the washing went straight into the ground.
And there's a big plume that extends downhill from the original location. It's like a waterfall of toxic chemicals coming down through the groundwater slowly. So it's a stain that's spread over that whole landscape. it's off-gassing up. Talking to students, I thought there would be more students, but talking about how people keep expecting them to solve the problem, but that's unrealistic. We have to start solving the problem now. We have to solve the problem, not expect people who are coming into their careers as junior staff to solve the problem. And we're seeing the record high emissions level. So we have not yet reduced the amount of emissions on a global scale. And that has this, puts this incredible pressure on us because we know today what we'll have in 2100 as a result of today. And I don't think that's ever happened in human history. People have been able to speculate, oh, what if the Roman Empire collapses? Oh, what if the Persians take over? Oh, what if this? No, this is happening as a result of what we've done to today. And it can only get worse. At this point, we're on the yellow train. Maybe the orange train, and that means we're going to be at 2.5 or 2.7, really 2 to 3.5 in global average temperature in degrees Celsius. We are no longer on the 1.5 train. It's inaccessible to us.
Well, did you say there's you know it's going to happen in 120 years? Was it?
Yeah. Well, this is 2100 on this particular graph. These people do our carbon budget globally. And they connect it to all of the climate change modeling to predict just global average temperature. Even if we stopped all carbon emissions today, we probably will get to 10 feet of sea level rise because of ice that's been set in motion melting. So even if we could completely stop the train and not have temperature go up at all from today, we're at 10 feet at some point. It's just a question of whether it's 75, 150 years, 300 years, but we have already committed. That horse has left the barn.
What the effects that we're having today? When were they produced? As in, like, were they 1970s emissions? Or?
Probably. I don't know the answer to that question. Probably.
Well, I guess there's no point. It's better to.
There was a huge doubling of emissions, like as a volume, if you think of a cumulative graph of all emissions in the 1980s. So even after the United States knew so much about what it was that we were doing, we knew in the 80s.
Seems more complicated than like when, like a certain time when it started.
It started in the 1840s. And since then, it has really gone off the rails.
Yeah.
You said 1840s.
With the first coal-fired engines
In the U.S.
in England.
Yeah.
And shortly in the US right after that. The first coal.
Human induced.
Yeah. And we reversed the trend. We were getting colder. And we have reversed the trend completely.
Oh, yeah. How?
By putting all the CO2 in the atmosphere. I mean,
Oh,
how
so-
are we getting colder?
Yeah.
Natural cycles.
Okay.
Like we were probably headed for a mini ice age or something. So we've been learning from the Dutch because the Dutch do a lot of engineering. They mix their government, private sector, universities, and they focus on the facts. And the facts for them have been that 45% of the country is under sea level, and they need to know how to adapt. Otherwise, they're all moving to Germany, and they don't want to. So they're doing lots of stuff, and they're doing lots of pilot projects. They don't have the biodiversity we have, so they're not as focused on doing anything possible to stop shading the near shore. They just throw sand around. They are not focused on biodiversity. But they know that as sea level rises, groundwater also rises. This is from a 2009 report from the city of Rotterdam. Our US Geological Survey started focusing on this first in 2012. And the Dutch have known for 100 years that this is going to happen. So what is groundwater? It's that stuff when you dig down at the beach and you find water in the sand, that is groundwater. This is the best visualization I have. Because it's not seawater, it's fresh water making its way down and then mixing with water that comes in from each wave swash, but it's fresh water in the sand. And it looks like this in geological illustrations. We're talking about the saturated zone in the soil, where all the little pore spaces are full of water instead of air. And the top of that saturated zone is called the water table. I don't think that's a very helpful word. It doesn't express that it's a volume that's filled with water. It sounds like a surface.
Will groundwater always be fresh water?
No, eventually groundwater will be salt. Here's the salt there. So see how the ocean is, it's that stipple area, that's saltwater groundwater. And it comes under the land. It actually extends even farther. This is a weird scale in the drawing. You have to think of that distance from here to here as potentially as much as 3 miles. So it's a weird scale. So as the ocean gets thicker and heavier, it pushes that stipple toe farther in and up. So it gets thicker. The saltwater wedge is what it's called, edge. Every foot of sea level rise is a foot of groundwater rise. It's a 1-to-1. And it will taper going inland from there, but it could extend, let's say in the saltwater wedge extends a mile inland. And over that, it's 1-to-1. Groundwater rise, sea level rise. Farther than that mile inland, it'll taper down to 1 inch of groundwater rise with a foot of sea level rise. And then finally, no effect. So there's a big taper zone that could be 2 miles inland or more.
Okay, I'm kind of having trouble understanding this. So like, for example, say I have a farm in Sunol, which is where I used to have a farm. So the groundwater, I mean, it's not like an actual, I mean, there's soil, where you have the land surface and then the sea level fresh water.
Yeah.
Like that's also, we're talking about soil, we're not just talking about water there, right? It's not like land is on top of.
This is all soil.
Yeah.
Everything under this section mark.
Okay, got it.
This is all what
It's
we
like-
might call sediment in geology, because it's not necessarily got organic matter in it. That's what I think of as soil.
Yeah, it was just interesting to think of it almost like, what if I changed the way I thought of it and thought of it more as water with soil
The soil in it.
in it?
That's what it's like below the water table. It's that diagram of all the soil particles saturated with water.
Mhm.
Great thing for plants,
Yeah.
because the plants can use osmotic pressure to pull that water up. That's the point of roots.
But when you get salt water, like when you get sea level rise, and we're talking about more salt water intrusion
This
into
toe is gonna come farther inland, and this saltwater boundary here is gonna come farther up.
So that could, like, when we think about that 10-foot rise in sea level, how are we talking also about saltwater intrusion into our farmland?
Yeah.
It's like how, like, okay, so 10 feet of sea level rise. Do people also know how far that saltwater intrusion is gonna go? Like, is it gonna affect
There's a
the
model.
Central Valley?
The US Geological Survey is showing the model. It won't affect the Central Valley. Well, wait. It will affect the delta depending on what we do. We would have to block the tides from coming up the delta to prevent saltwater from entering the delta. Once saltwater enters the California Delta, it will affect water supplies, irrigation,
And food.
and food. But, a lot of export food too. It's commercial farming, it's not like subsistence farming.